So, in Lecture 3, we're going to continue talking about computational Boolean algebra, but we're going to focus on real, practical data structures and operators that are basically the foundational methods that everybody uses to do large industrial scale sorts of designs. When we talked about the unate recursive paradigm at the end of the last lecture, we introduced a simple kind of a representation in just one basic operation, tautology. URP is a historically important representational scheme, but it's not really the way we really do things today. So what I want to start talking about is one of the most powerful data structures in the Boolean universe, and that's the binary decision diagram. So they're called BDDs. And in this lecture, we're going to introduce what a decision diagram is, and then we're going to start manipulating it and restricting it and constraining it so that it becomes a really powerful data structure on which we can do important operations. So let's start.
So here we are again focusing on representations and how important they are in our study of computational Boolean algebra, where the goal is to be able to manipulate Boolean objects as data structures that are operated on by operators that we can build in software. And as a way of example, I'm just showing you what we ended up with at the end of the last lecture, which was the URP tautology algorithm. And you know, this is really a great warm-up example. I've just got a little example on the right here. We've got an internal node in a tautology computation that has cubes B, C, and B bar, C bar. So it would seem that we've already had A set to 1 before we got here. We cannot tell anything about tautology for this particular collection of cubes, so we're going to have to go a little further. Set B equals 1 on the left-hand side, set B equals 0 on the right-hand side. Do the cofactoring we see on the left-hand side. Oh, I can tell it's a tautology because I've got an all don't cares cube. There's a 1 in there. And on the right-hand side, we can again see it's tautology because we've got two single variable cubes, C and C bar. And when we OR those together, we get a 1. This really does show the big idea of Boolean functions as things we manipulate with software. But I have to admit that URP is, you know, it's not the real way that people do it, or it's not the most popular, the most influential, the most widely deployed way. It's not one of those. So what we want to do in this sequence of lectures is look at a really important, elegant way to do this, a really powerful and interesting way. These things called binary decision diagrams. So let's talk about those. Now, decision diagrams were actually studied by lots and lots of people, Lee and then Boot and then Akers way back when. But they got seriously useful when Randy Bryant of Carnegie Mellon University made a really remarkable breakthrough. And so these things are technically called reduced ordered BDDs or row BDDs, although honestly, everybody just calls them BDDs these days. This was really the breakthrough that made these things useful as a remarkable data structure. There's a big and interesting Wikipedia page on these that's certainly worth looking at. And I'll also say that Randy provided lots of the nice BDD pictures in this lecture and some of the foundational structure of this lecture. So big thanks to Randy Bryant for letting us use that material. So our first step in the development of reduced order BDDs is just to talk about what a decision diagram is. So the first big idea is just to turn a Boolean function into a decision diagram. And you can kind of think of this as taking the truth table, and I've got one shown at the upper left, and kind of turning it on its side and putting it in the form of a tree. So this is a truth table for 3 binary variables, x1, x2, x3, and so it's got 8 rows. The first 4 are 0, 0, 0, 1, and the second 4 are 0, 1, 0, 1. And the big idea of a decision tree is that it answers the question, what is the value of the function as a sequence of decisions? So every vertex represents a variable, and so here's a vertex that represents the variable x1, I've just got shown here. And the edges that go out of those vertices are decisions to set that variable to a value. So if you follow a dotted green line, then you've decided to set the value to a 0. And so I can say over here, x1 equals 0. And if you go on a solid red line, you've decided to set the value equal to a 1. So I can write x1 equals 1 over here. Now, all of these arrows are really directed. They're all going down. But by convention, we just don't draw them because we know where they go. And the answer is that they all point down. Right? So I don't really need to draw that. And then the idea is that you follow a sequence of decisions as you move through the variables and out their edges until you have visited all the variables you need to be able to make a decision. So for example, the first row of the truth table, and I'm just going to highlight it like this, the first rows of the truth table, you'd say, well, if x1 is 0, now what? Okay, well, now I need to know something else. Okay, well, if x2 is 0, now what? So, well, I need to know something else. Well, what if x3 is 0? Oh, well, actually, I know enough to tell you the value of this function. The value of this function is 0. That's just that row of the truth table. And this very simple decision tree, which completely defines every single row of the truth table as a unique path through the decision tree, just kind of maps out the truth table. So it's really going to be 0, 0, 0, 1, like the first 4 rows of the truth table, 0, 1, 0, 1, like the next 4 rows of the truth table as we map that decision tree out. So that's really all there is to a decision tree. It's kind of like a truth table turned on its side, rendered in the form of a sequence of variable value decisions until you can tell me what the value of the function is. So there's a little bit of terminology. We can just walk through that here. We talk about the vertices, but we just tend to call them variables. That just makes life easier because they're all associated with a variable. And we often talk about the edges that come out of a node as being pointers, because they are. And sometimes we talk about the low pointer as being the pointer that's what happens when I assign the value to a 0. We also talk about the high pointer or the high child as being what happens when we assign the value to a 1. And a variable ordering is just the order in which the decisions about the variables are made. So I'm just circling that, a big one right here. x1 gets a decision, and then x2 gets a decision, and then x3 gets a decision, and then we know enough to actually tell you what the value of the function is. In this case, it's a 1. That's called a variable ordering. And the things at the bottom are called constants. Right, no surprise, because they're not variables, and they're also the leaves of the tree. They're the things that you get at the bottom when you can't go any further and you don't need to visit any more variables. Now, one of the things to note is that different variable orders are possible. I mean, I haven't said anything about why one would choose a particular variable order. I mean, I did it in a somewhat obvious manner here. All of the x1s are at the top of the tree, and then the next level are x2s, and then the next level are x3s. But there's no reason that I had to do that. I could have flipped that. So in this particular example, after I choose to say, let's set x1 equal to 0, I could decide that x3 is the next variable that I'd like to look at, and then x2. And in this case, I'm going to get a different tree. In this case, when x3 is a 0, then it doesn't matter what x2 is. The value of the function is a 0. And when x3 is a 1, it also doesn't matter what the value of the function is. Sorry, it also doesn't matter what the value of x2 is. The value of the function is a 1. And so this is a different tree. No surprise. And that's going to be a problem. So let's make a few observations about this. First, every path from the root to a leaf traverses the variables in some order. That's not a big surprise. Each such path constitutes a row of the truth table. So that's a decision about what the output is when the variables take particular values. So that's interesting. It's sort of a very different way on evaluating the rows of the truth table. But we have not yet specified anything about the order of the decisions. I have not constrained ourselves in any way. And as a consequence, a big thing happens, and it turns out to be a not very good thing. The decision diagram is not unique for this function, and that's not helpful. And one of the big things that we're really going to be shooting for here is something that's called a canonical form. Now, a representation that does not depend on the gate level implementation of a Boolean function, that's what canonical means. So if you give me the same function of the same variables, it always produces the exact same representation. In this case, a data structure. So for example, a truth table is canonical, and I'll just say this, up to order, right? And what that really means is that as long as you tell me the value of the variables in the top row of the truth table, as long as you tell me, well, there's A and then there's B and then there's C going from left to right, if I make the function as a truth table and you make the function as the truth table, we will get exactly the same truth table. It's canonical. What we really, really want is a canonical form data structure, so that if we both agree on what the Boolean function is and we both build it, we get exactly the same data structure. So what's wrong with this diagram representation? Well, several things. It's not canonical. That's a big one. But honestly, the first thing that's really wrong with it is just way too big to be useful. I mean, it's as big as a truth table. If you had a function of 100 variables, you have 2 to the 100 rows. That's just not happening. And in this particular decision diagram, you have 2 to the 100 leaf nodes down at the bottom, and that's not happening. I need a better order. I need a better idea. And so I'm gonna impose some structure on things, and we're gonna see where that takes us. So the next big idea after just the first one, which was let's make a decision diagram, is ordering. And in this particular case, we're gonna restrict the global order of the variables. And so what that's going to mean is that every path from the root to a leaf visits the variables in, and then I'm going to write it big, the same order. Now there's a little technical point here, which is that it's okay to omit a variable if you don't need to check it to decide which leaf node to reach for a final value of the function. So you have to visit the variables in order, but if you skip some along the way, that's okay. That's not a bad thing. And we'll show that as a quick example next. So what does it mean that there's a global ordering of the variables in a BDD? It means we're going to assign a total order to them. So for example, in this case, let's assume the variables are ordered x1, x2, x3. And that's what the less than signs mean. It means in order of. x1 will appear before x2, x2 will appear before x3. The variables must appear in this specific order along all paths, but it's okay to skip variables. So on the left, we see just a nice simple example. x1 appears, and then x2 appears, and then x3 appears. So that's perfectly okay. But the one on the right-hand side is also okay. There's no x2 in there. So x1 appears, and then on a path from the root to the leaf to a leaf, there is no x2. That's fine. x1 shows up before x3. Everything is good. The examples on the right are things are examples of bad things. So this one is just wrong. This one is just wrong, right? x3 can't come before x2, and x2 can't come before x1. And there's no other way to say what the one on the right is. This is just stupid, right? How can I have a decision diagram where I make, in this case, x1 equal to a 1, and then change my mind and make x1 equal to a 0? That's just stupid, right? So the properties here are that we're looking for, there are no conflicting assignments along the path. That's what that rightmost example that I just showed, that's a conflicting assignment. You're going to see each variable at most once on a path, right? Never twice, and you're always going to see them in the same order. So suppose we go back and we say, I insist on an x1, x2, x3 order. Now what? Right? So this decision diagram over here is still okay, right? It's not doing anything illegal, but the diagram on the right is also okay, right? And it is equivalent. It is the same function but different, and that's a problem. Right, because note what happened here. What happened here was there was an observation. If x2 is a 0, then, as we go here, if x2 is a 0, then we look at x3, and the value of the function is x3. x3 0, function makes a 0, x3 1, function makes a 1. If the value of x2 is 1, same thing happens. x3 makes a 0, the function's a 0. x3 is a 1, the function is a 1. I don't really need x2. x2 is not really providing me any value. If I make it go away, I can substitute this very different diagram, which has on the left still the sort of the full original tree of the very simple version of the decision diagram, but it replaces the entire right subtree with its 3 nodes with a single x3 with a 0 and a 1 underneath it. Well, obviously this is not a canonical structure because both of these decision diagrams represent the same Boolean function, and as I said previously, the big thing that we were looking for was no two different diagrams are allowed to represent the same Boolean function. So I need another idea. I need another constraint. So in the next talk, we're going to add another constraint, and we're going to see how well that does in making our binary decision diagrams canonical.